Thank you, Dr. Kropchak. I'm Jeff Myers. I'm with the university's Tech Transfer Program, and I'll be introducing each presenter this morning. They'll each be telling you about their innovations, and we've got some fascinating presentations, some really good inventions that are ready for commercialization or already underway in the commercialization process. And we're just about on schedule now, so without further delay, let me introduce our first speaker, Dr. Samir Aouadi from the Department of Physics in the College of Science here at Southern Illinois University. Dr. Aouadi, I've known him for several years. He's been a prolific researcher, and today he's going to talk about his novel smart coatings for high-temperature lubrication.
Okay, thank you very much. I'm really excited to be here today. My talk is on smart coatings for high-temperature lubrication, and I'm a professor here in physics, and I'm proud to report that I just filed paperwork to start a company, Adaptive Coatings LLC, and I'd like to thank Kyle and Lynn and Amy for inviting me, and for the class Mousetrap. That's what has helped me with starting this company. So the problem here is friction and wear in moving assemblies in jet engines initially. So if you have a jet engine, you have at least 35 to probably 50 or 60 moving assemblies. And you have a lot of problems with friction and wear. And so in my lab, we have created a new coating that's able to extend the life of jet engines by at least a factor of 10. So if you don't have to replace these engines, that would be great. One of the coatings that are really interesting that I'm going to talk about towards the end, they're called smart chameleon coatings, and they do not exist currently in the marketplace. And they are basically like a chameleon where their skin or their surface basically changes as a function of the environment that they are in. So I'll get into to that in a few minutes. So the first application is on the far right is a jet engine, for example, for bearings and things like that. You can reduce the friction so that they can last longer. The other application that's really important for the military, and I just got this summer project or a grant from the Air Force Office of Scientific Research, is for hypersonic aircrafts. So basically the Air Force are trying to create these aircrafts and missiles that can reach anywhere in the world in 45 minutes to an hour. And you can imagine how fast these are flying. So if they're flying at Mach 6 and higher, up to Mach 20 and Mach 25, you can imagine that with the friction with the air molecules in the atmosphere, the skin of these airplanes is going to reach at least 1,000 degrees Celsius or 2,300 degrees Fahrenheit or above, so depending on how fast it's going. So we're trying to make coatings for them, especially for external moving assemblies, let's say for the rudders, for example. That's one example. So for the rudder, in order to turn left and right, you need a smooth, lubricious coating so that so that it doesn't jam. Other applications of these coatings that I'm working on are for automotive engines, for the pistons, for example. So we have a project with Bosch from Germany that we started last year, and we're making coatings for them as well as for the tooling industry. So how do these coatings work? Basically, you have two rubbing surfaces, and you have a load. So you have a load between them, and you have a lot of imperfections between the surfaces. And in addition to that, which is what I'm focused on, is high temperature. High temperatures can be, like, I'm interested in 1,000 degrees Celsius range or even higher, and eventually. And so what we are doing is we're modifying the surface of these materials with a coating that has a low friction coefficient. Okay, so that's basically the projects we're working on. Now, this is called tribology. Tribology, you go to any hardware store locally, you can buy lubricants. For example, you have greases and liquids and things like this. But you can also buy what's called solid lubricants. And these are graphite, and you can buy also moly. It's really molybdenum disulfide. And you can buy them in a can or in various forms. And the reason why these materials work is because they have the crystal structure that you see on the far right, where you have planes of atoms, and these planes of atoms have weak bonds between planes, so they can shear easily. So if you apply a load on them, they shear and therefore have a reduced friction coefficient. The problem is at high temperatures, no such material exists so far. Okay? And so what we did is we said, first, we can't use graphite or molybdenum disulfide because they're going to oxidize and they're not going to be good. But at the same time, we wanted to use oxides because everything in atmosphere is going to oxidize anyways. And so the materials that we selected were all silver-based. And the reason why is silver-oxygen bonds, silver doesn't oxidize readily, so silver-oxygen bonds are very weak. And so if you have them in a crystal structure like you have on the top there, those bonds are so weak that if you apply a load on them, they can shear, just like the graphite and moly disulfide. And they can also perhaps melt because these bonds are so weak that they're not going to have a high melting point like most oxides. Okay. So we started by working on these, which are usually, that's counterintuitive because most oxides are usually abrasive and not have a good friction coefficient. So we started working on these, and these are, the reasons why they would have good friction coefficients, which I explained a few minutes ago. And the way we make them in my lab there's two methods. The first one, which is not really my strength, is more chemistry, is using what's called hydrothermal methods. And the hydrothermal method is basically you have this autoclave, you add some chemicals in it, and you create this oxide. It takes 24 hours or more. And this is a scanning electron microscopy picture. You can see that you have these powders that are small scale, like nanoscale. These look like brooms. And basically, you can burnish them on a surface, and you can have a low friction coefficient that way. The other way, which is my strength since I was a grad student, is using what's called sputtering, which is a technique that's an expensive technique because you have to buy a sputtering machine that costs, a smaller one is $100,000 or more. And you're basically sort of like evaporating these materials onto a surface. So you're evaporating, this is your surface, and these are your sources. And so let's say you want to deposit titanium, you deposit titanium, you evaporate that titanium onto the surface, and if you want to make, let's say, silver, molybdenum, oxygen, you have a silver source, a molybdenum source, and then in an oxygen environment, and they combine to form this silver molybdate, which is the binary metal oxide that has low friction coefficient. Okay, so that's how we make these materials. And then what we do to them is we test them. So in order to test them, we use what's called a pin-on-disc test. So you have this, or a wear tester. You have this disc. We put the sample on the disc, and we rotate it at, say, 200 RPM or something like that. And then we have a pin when we apply on the pin a load. So you put a pound or something like this of a load. And you have here sensors that measure the friction coefficient. And you also get a wear scar, a round wear scar, because you go over this, I don't know how many cycles, 10,000 cycles, 100,000 cycles, etc. And so then once your test is done, you get your friction coefficient. This is the first one that I got in 2007, 2008 when I started working on this project. So we have a friction coefficient of 0.1 at around 1200 degrees Fahrenheit. And then what you do is you look at the wear scar. You look at the wear scar with the profilometer, and you see in this particular sample, we didn't have any wear. Actually, there was a little bit of material buildup. The reason why is this silver is a little more mobile. It doesn't stay in the crystal structure, and so you have the mobility of silver that goes to the surface as well. And so this was the first best coating that we've made, like I said, in 2007, 2008. Okay, since then, we've been doing a lot of the similar work with various other metal oxides. And these metal oxides include, for example, silver vanadium oxide instead of silver molybdenum oxide, and silver tantalum oxide. And this is the focus that we're working on now with the Air Force. We're getting such low friction coefficients of 0.06 that's unheard of. This is a world record in terms of friction coefficient. The program manager is so excited that he went to NASA Glenn in Ohio last week, and he called us from there, and he wants us to take these samples and get them tested there. So this is really exciting for our group. And the other thing that we worked on are, so the oxides that I've been talking about so far are non-adaptive. So they're basically good once you reach about 1,000 degrees Fahrenheit or above. They don't work as well at low temperatures. Now let's say if you want to have a material that has low friction in any condition, how do you do that? So that's challenging. Well, the way you do that is by having what's called a chameleon coating. So you mix materials where one of them, for example, here you mix a nitride, a molybdenum disulfide, and silver, so 3 phases or 3 different materials together. One of them works well at room temperature, the moly that I talked about earlier. The other one works well up to about 1,000 degrees Fahrenheit, so works in the mid-range temperatures. And then finally, you can also form silver molybdate if you heat it or if the sample is hot enough. And the way that works is, this is how it works. So some of the silver, some of the molybdenum gets to the surface and forms this nice silver molybdate only on the surface, and that's what lubricates at high temperature. And then once you go back to room temperature, this gets worn out quickly because it's only very thin film, and then you have the other stuff that's good for at room temperature. Okay, so the other thing that's really interesting about these materials is it would be easy to scale up because sputtering, although in the lab I make it in a small machine, these machines already exist, and you can make these oxides or nitride, whether they're adaptive or non-adaptive, very easily. And that's the thrust for me, like why I wanted to start a company as well. And basically, also, in order not to waste a lot of time, my colleague from the University of California, Merced, is working with me on this project, and she does basically simulations. So these are atoms of these silver molybdenum oxide or silver tantalum oxide. How does it shear? How, like if you increase the temperature, what happens to the atoms and things like this, and it explained basically. So instead of going and making a lot of samples, which is much more costly, you can do the simulations, and then from these simulations you figure out, okay, these are the choices we have, and let's go ahead and understand why they are so lubricious. Okay, so the opportunity here to start a company is there are no adaptive coatings in the marketplace. Not only that, there are no binary metal oxide coatings in the marketplace either, actually. And there is a 30 to 50 billion annual sales for space and aerospace industries. Actually, I just visited General Electric. They also make jet engines for the airplanes in August. And I've heard from them that they're building a facility in Alabama that's mostly for coatings, so coatings for jet engines. And they're going to have at least 35 families of coatings for various assemblies and for protection, et cetera, et cetera. So that's really exciting for us. So the customers that we have lined up so far are Rolls-Royce Corporation, which is in Indianapolis, and we started working with them already. The U.S. Air Force at the Wright-Patterson Air Force Base in Ohio. Robert Bosch, which is in Germany. We're working with automotive engines. Those are not as challenging in terms of temperature because the automotive engine doesn't go above about 500 degrees Celsius or something like that. And then there is a coating company in Dayton, Ohio that has done a lot of work for the Air Force. So my idea is to have a company where I don't do the coatings, but I would just be the liaison between the coating company, which is UES in Dayton, Ohio, and the end users, which are the military and the jet engine manufacturers as well. So just before I finish, I just wanted to add that these materials that we've been working on, in my lab, we also do other things, which include a lot of surface science and engineering. So basically, we modify the surface for various functionalities, and these include, oops, making the same mistake, includes a thin film, nanodots on the surface, texturing on the surface, functionalization on the surface, and also making nanowires, nanotrees, and the applications of all these technologies, what we're able to carry out here at SIU, include surface modification of coronary stents. So we take stents now that are not working as well, and we're trying to functionalize them so that we have endothelial cells attached to these surfaces better. We're also, these nanotrees that I just showed you could have an impact on photovoltaics research and for large-scale manufacturing. So if you have a web coating, even whether it's a sputtering or another technique, you can have a cheaper or less expensive way of making photovoltaic research. And then finally, with the Air Force as well, we're interested in modifying the surface of these hypersonic planes so that with thermoelectrics, so that with these thermoelectrics, you have a high temperature gradient. You can create electricity and power up these aircrafts as well. So, as a summary, I just want to say something that I'm very biased about, which is material science and engineering is very important. Everything that surrounds us is materials and radiation. And so the U.S. Department of Commerce has identified advanced materials as one of the most important, or the 5 most important and emerging technologies in the United States. If you look at Asia, for example, their #1 area where a lot of funding is carried out is in material science and engineering. We work mostly in my lab in surface science and engineering, and we try to do both basic research, where we're trying to understand why these materials are better performing, but also we're also market oriented because we want to do applied research where there will be creation of new products. We do mostly what's called thin film deposition, so we do coatings, and that would be for tribology, friction, biomaterials, and energy, everybody. I mean, it's a very important area to work on. And we try to focus on innovation. What can we do that nobody else has done, and we do it better than them. And we stress also successful collaborations. My lab alone cannot do it. I can't do it on my own. because we have our strengths, but we also have our weaknesses. And so we rely on theorists to do simulations to understand what's going on engineers and scientists to work together. And then we're working also with the military national labs and also with industry. Thank you very much for your time and attention. Any questions? Yeah, Gary.
Do you hold patents on this technology?
Not yet, and that's a problem. I agree. Yes.
Anything else? All right, thanks, Samir.
So I have a question.
Sure.
There's one.
You are counting on the silver to migrate at the surface. The kinetics, you don't control it. It's basically the intrinsic interaction of the atoms
Right.
that leads silver to go to the surface.
Right.
Can you control it? Is there any mechanism that can be put in place in such a way you control or you dose the effect, say how much silver do I need on the surface to be able to achieve?
Yeah, honestly, that's a very, very good question. There is, and I've heard that from companies like GE, they're a little wary of silver because it can get into other areas. And so that's, you can do the same thing, not just with silver, you can do it also with copper. You're not going to have as good of a friction coefficient. That's one. Two, that's why we're focusing on the silver tantalate. That one, we didn't see that much migration of silver with the silver tantalate because it's a stable phase compared to the silver molybdate or silver vanadate. So that's why I'm staying away a little bit from the first two that we started off working with in 2008 until recently. But this new material that the Air Force is really excited about is very stable, that even the silver itself doesn't migrate as much. And I didn't bring with me here some pictures. My colleague is doing some simulations too, and we see that silver tantalate doesn't migrate either. So that's, you see, so I think that's better.
Okay, great. Thanks very much.
Thank you.